We are now introducing our paper 3D Gaussian Inpainting with depth-guided cross-view consistency. So the task of 3D scene inpainting is to remove something we don't want in a 3D scene and inpaint the artifact or blurry hole left by removing the object to be as real as possible. Typically, the input are multi-view RGB images of a scene, and the corresponding binary masks of the unwanted object also provided. Previous methods tried different approaches by either separately inpaint each view or just inpaint one selected reference view and then project the inpainted results to other views. Some even use LoRa plus adversarial loss to make sure the inpainted region to be realistic. However, we found that very few of them look into a very foundational problem. Is it proper to inpaint everything in the given 2D masks? We visualize this bare scene trained by 3DGS and removing the 3D Gaussians corresponding to the bare. We can see that most of the background is observable, and only a small region on the stone here is blurry, which is much smaller than the bare's object mask no matter in what camera pose. The actual region needed to be inpaint is the region that is not observable in all camera pose. So if we directly inpaint everything inside the bare's object mask, we can see that on the upper branch that background contents are modified. This will lead to inconsistency of the background after inpainting. On the other hand, if we can locate the actual unseen region to be inpaint, the background can be well preserved while the foreground is inpainted properly. So we propose the 3D GIC to achieve two goals. The first one is to inferring proper inpainting mask for each view that preserves background content, and the second one is to use a single reference view as guidance and force other views to refer to the reference view to enhance multi-view consistency. Take the bare scene as example. We use the multi-view image to obtain a pre-trained 3DGS scene with Gaussian grouping as backbone, and the object mask is also obtained by the segmentation results of Gaussian grouping. We also render depth map for each view for further usage. Specifically, we design an inferring depth-guided inpainting mask process to obtain inpainting masks that preserve background contents using depth-guided projection. We also design an inpainting-guided 3DGS refinement that takes a single view's 2D inpainting results as reference to ensure cross-view consistency. I will detail each these two components. So taking view number 1 as example. Our inferring depth-guided inpainting mask process extract background pixels from other views, which is the RGB pixels except the bare. We then use the rendered depth maps we obtained earlier to project the background pixels in other view to view number 1. And we see if the projected pixels lie inside the masked region in view 1. If so, we update the masked image, mark the corresponding pixel position in current mask as 0, which means the background of this pixel is observed from other views. By doing so, the mask will become much smaller after seeing all other views. Here's a visualization of this process. After we obtain proper inpainting mask for each views, we can now apply inpainting. So to initialize the 3DGS model to be inpaint, we first remove the Gaussians corresponding to the bare. Then we will select a view as reference view, let's say view number 1 again. We inpaint the RGB image and depth map rendered from the 3DGS model without the bare, using the previous obtained depth-guided mask as inpainting mask. The inpainted RGB image of view number 1 is like a golden standard for inpainting the whole scene. So we projected the inpainted regions in view number 1 to 3D space using the inpainted depth, denoted as P1. And since it is likely that the stone surface does not have much Gaussians after removing the bare, the projected 3D points position of P1 are used to initialize some new Gaussians on the surface of the stone. As for the optimization, for view number 1, the rendered image and depth map from the refined 3DGS model should be strictly follows the 2D inpainted results we obtained earlier. So pixel-wise losses are applied. As for other views, we project P1 to each view and only calculate LPIPS loss since the projected points are just some kind of reference. And of course for the regions outside the inpainting masks, L1 loss is still applied to make sure the background are not modified. Here's our quantitative results. We compare our 3D GIC with multiple state-of-the-arts and show superior performance in terms of FID and LPIPS. We also show some qualitative results of different datasets. This one is figurines, seen from NeRF dataset. This one is counter, seen from MEEP NeRF 360 dataset. This one is kitchen, seen from MEEP NeRF 360 dataset. This one is bare scene from NeRF 360 dataset. And here's the ablation. The baseline is using the original bear's object mask as inpainting mask and apply 2D inpainting on all views, then refine the 3D GS using the preview inpainting results. We can see that a very large area in each view is still blurry after inpainting, including the background. As for Model C, without our depth-guided mask, high fidelity is observed but with inconsistent background. As for Model D, although the background is now preserved but foreground regions are blurry. This shows the effectiveness of all our design strategy. In conclusion, we propose a depth-guided 3D inpainting framework for real-world scenes. By inferring depth-guided inpainting masks, we can preserve background content properly. And using a single-view 2D inpainting to guide 3D GS refinement, we achieve cross-view consistency for the final inpainted 3D GS model. And that's all, thank you.